So my presentation is on current approaches and future directions for point cloud object detection in intelligent agents. So to try to frame all of this, just so everybody's aware, we have a broad audience today. So my presentation is going to primarily focus on the entrance to these sort of approaches, i.e. the representations and how you initially process them. A lot of the detection heads and stuff tend to come from the vision literature. So if you're not a vision person, you don't have a vision background, the goal is to get some sort of high-level intuition. Additionally, I'm going to then talk about the literature itself, i.e. the presentations in the paper, discuss what they do talk about and what they don't talk about, and what the implications are for someone who's trying to build a real robot. So hopefully that sort of gives you a roadmap for where this is going to go. And with that, let's get started. So the very first question is, what is a point cloud? This is a point cloud. So this is actually taken from a self-driving car, and it was taken with a LiDAR laser scanner. So essentially how this works is there's this collection of 3D points representing the surface of objects in order to represent a scene. So you can see these sweeps across the ground here. These are the laser hitting the road in front of it. You can kind of make out a car. These are businesses along the side, another car, another car, another car, right? This was taken in a semi-urban area from the KITTI data set. So the next question is, what does point cloud object detection look like? So for the purpose of this work, we're going to consider regressing bounding boxes and then providing a class label to said bounding boxes as the problem of object detection. So as you can see here in this picture, all they've done is try to recognize cars, right? This is one of the 3 classes that are trying to be detected in the KITTI data set. So how is point cloud object detection evaluated? So as I've mentioned, the KITTI data set and other data sets exist. They provide an input, right? The raw point cloud. You run it through an object detector and it regresses bounding boxes. And then it compares them against the ground truth, which provides an actual labeling of what boxes are there, right? So this is a supervised learning problem. And the goal is to try to build this object detector, either by learning or some other means. So in terms of actually evaluating this, oftentimes these data sets all formulate the problem the same way, right? They care about IOU, which is to say intersection over union. So the intersection of these 2 bounding boxes is the green plus blue area in here. The union is green or blue. And the idea is, as long as you have above a certain threshold, typically 50% to 70% overlap, the box is considered to have been a positive match. And it then takes any other boxes that the method also proposes, right, relative to the ground truth, and says if they're the non-maximal estimate, those are going to be considered false positives. So you have the ability to evaluate true positives on your relative to your ground truth labeling. You have the ability to identify false positives, and though this allows you to compute average precision, right? True positives divided by true positives over false positives for a given class, and then you can compute the mean over all of these. And you can do other things like, for instance, compute average orientation similarity, which also measures angle with AP, right? The primary takeaway here is there's a bunch of different data sets, which I'm going to talk about in a second, but they all pretty much evaluate this problem the same way. They're basically trying to measure how well your bounding boxes line up. Right? That's essentially the key takeaway from this slide. So I mentioned KITTI several times now. It's the most famous and most popular data set because it came out in 2012. Right, this is the same year that AlexNet came out. AlexNet essentially kicked off the deep learning revolution in vision. And it is fairly small by today's standards, but it was big at the time, right? There's 15,000 labeled point clouds. And typically what they do is they split them into 7,500 as training, 7,500 as test. And because this is a relatively small data set by today's standards, there's a lot of data augmentation that you need to do in order to perform well. In order to try to remedy this, people have developed new data sets. So Argo, a self-driving car company, released Argoverse in 2019, right? 11,000 objects for 15 to 30-second clips. New scenes from Newtonomy, right? 1 million objects, and then Waymo, 10 million objects. So these are of much larger scale. However, because they came out recently, most of the literature that we're going to talk about today does not consider them because they came out contemporaneously. So with that in mind, where are we going from here? All right, so hopefully you have some notion of the problem. The goal is to then talk a bit about background for convolutional neural nets for those who aren't super familiar with them, just to bring you up to speed. Then I'm actually going to dive into the papers that we actually talk about for this work, right? So I would say one of the key synthesis components is this taxonomy, where we're comparing the different representation inputs. Then finally, we're going to transition and say, okay, we talked about these plus the literature associated with them, right? So I'm going to talk a little bit about each paper and what the evaluation sections and the presentation allow you as a practitioner to get out of those papers. We're then going to talk about what does it look like if you're a practitioner and you want to actually build one of these things for a robot. And then finally, we're going to talk about the gaps in the literature, right? What does the literature not allow this practitioner to do? And then future directions of research associated with that. So with that, I'm going to dive into the background. So essentially, every image that you've probably seen can be thought of as a 3-channel RGB, right? Red, green, blue image. So you can imagine there being an array of pixels, and each pixel has a red, green, and blue component that can be thought of as a 3-dimensional vector. So a convolutional filter over that essentially takes each component, multiplies by each element in here, and then sums all of these up to get a single value out. And so it used to be the case that people would hand build convolutional filters like this as feature extractors, right? They'd manually build these things and stick hundreds of them onto your image in order to get out useful features that they could then run through something like a support vector machine or something else to actually do classification. So you would essentially run this convolutional filter over each patch in the image like so. And as an example, you can take my face, run different feature extractors that would end up highlighting different regions of this picture, and then ultimately use them for this sort of classification problem. But you can imagine, rather than directly running these filters, doing very low-level local feature extraction, you would actually want to do this several times over several different layers, where you get these local features out, and then you would then gather them again to get a higher level representation, gather them again and gather them again. This can, in the intermediary steps, right, is actually an n-dimensional vector. So it's not just a 3-dimensional vector. It can be of arbitrary size. And again, you can have an arbitrary dimension convolutional filter associated with it. So you do the same thing. And essentially, you stick all this together, learn it end to end. And that is essentially how a convolutional neural network works, right? So with that background in mind, we're going to start to look at the taxonomy of current approaches. So I think the most obvious thing to do is say, okay, well, I know how to do convolutions over 2D images. I have a 3D scene instead of a 2D image. If I could turn this scene into a 3D equivalent of a 2D image, then I can just stick it all into the systems that I already know how to use and go from there. And so that's essentially the idea of a 3D convolution. So you take your scene, right? This is a 3-dimensional scene, and you impose a 3-dimensional grid structure over it. And so rather than having 2-dimensional pixels, you have 3-dimensional voxels. So you can imagine them literally being cubes in space, where each cube is essentially a 3D pixel, and they're all the same size relative to one another. Or they can have different heights and widths, but or the width and the height need not be the same. So one of the neat things about this encoding structure is it doesn't matter how far away the voxel is from the observer, the scale is the same, right? So a half meter square is the same super far away as it is close, which isn't necessarily the case in, say, a range image, where because there's some sort of curvature to the lens and you like cast outward, as you get further away, pixels that are directly next to each other are now going to be further apart. Additionally, this representation, this 3D encoding, better handles occlusions. And the reason for that is because you're actually scattering it into this full 3D space, you're actually able to reason about the negative space where one object is sitting in front of another, which is much harder to do in, say, an image format. One of the things to note of this, however, is this representation tends to be sparse. And by sparse, I mean most of the voxels tend to be empty or have very few points. And this is particularly an issue at range, right? The further things get away, the more distance there is between the individual readings. And so the harder it is to do object detection. So we're going to come back to this in a moment because this is going to be important. But for now, imagine that we can take these individual voxels that had points floating around inside them and somehow turn them into a vector, right? And so this is essentially the same as what we had before with the image, but now we just have a bunch of these stacked together. And this will let us just run a 3D convolution. And so the neat thing about that is, okay, cool, I run the convolution just like before, and I can essentially do the same thing that we talked about with the 2D network. And boom, you get something kind of like this with a few more dimensions that you can run, right? And so that's essentially the really compelling reason to try to use these 3D convolutions. But I think a very reasonable open question is, how do you vectorize these points? And so this is going to be a recurring theme throughout this and other approaches. So this is justifying an aside, which is talking about point vectorization, and brings us to my first WPE paper. So in order to take these points and represent it as a single vector, we actually can go look at some of the other object detection literature. So a different formulation for PointNet, right? PointNet is the network we're going to use to solve this, is given a collection of 3D points, either with some occlusion, as you can see here, or full 3D points on the CAD model. The goal is to actually do classification, number one, and then two, in this case, do semantic segmentation of each individual point from the PointNet network. So this is the architecture, right? The idea is you have an unordered collection of points as input. You run it through these TNets, which we'll talk about in a moment, a multi-layer perceptron, a second TNet, another multi-layer perceptron. You then do max pooling, and you get out this global feature vector. So we can mostly ignore the rest of this because it's not really relevant. But the key property that we care about here is that each of these operations is identical run across each point. So that is to say, the input points could be shuffled, rerun through the network, and you'll get the exact same result because each multi-layer perceptron is run over a single point. And the max pool operation at the end doesn't care about order either. And what we actually get out is this global feature. So going back to our 3D conv problem, right? This global feature is the thing that we want. So I mentioned TNets briefly. So the purpose of these things was to try to take your input representation and rotate it into some canonical form that would be easier to solve, right? If you remember the original pictures, they were like cups or other things rotated. So these are actually very large networks trying to regress a rotation and translation matrix in order to try to normalize these things. So if you actually look in the PointNet paper, they look at how accurate this is for classification, right? Overall classification accuracy, given no transformation network, and then with both. You only get 2.1% higher accuracy, but the model is 4.3 times bigger and uses 3.9 times more flops. So the name of the game in these sort of models, right, when you care about applying them to actual robots, is being able to make trade-offs between performance, right, how high quality your output is, and runtime. And so as you might imagine, 2.1% performance for this task is not worth this dramatic overhead. So in practice, when people are using point nets to try to do vectorization, they chop all of these things out. And what you're actually left with is a very simple network, right? You have these input points. You don't do any sort of order-dependent operations on here. You run a max pooling and you get out this global feature. And this global feature is the vector that I talked about when I said vectorization before. And note that these sizes can be easily tweaked, and something that is briefly mentioned in one of the later papers is that this can actually be implemented easily via one-by-one convolutions. So with that in mind, we now have essentially VoxelNet, right? So VoxelNet is a 2018 paper from CVPR where you take your gridded input, right, your voxelized input, you vectorize each voxel, you then run a 3D convolution over it, you get your tensor, and then you stick it into faster RCN, which is a standard image detection network. And it'll end up, you can modify it and it'll end up regressing these boxes, right? So it sticks it into the region proposal network. Those propose gross bounding boxes, which it then does bounding box regression and then non-maximal suppression. This is the idea that if two boxes are near each other and overlap, you throw away the ones that are of lower confidence. in order to avoid having this false positive that we talked about before. And you get out regressed bounding boxes in position, length, width, height, as well as theta, which is rotation relative to the ground plane. So one of the things to point out about VoxelNet is the 3D convolution dominates runtime, but 90% of the voxels are empty. So this goes back to this comment I made earlier about sparsity. So we care a lot about making sure that these things run in an appropriate amount of time. And so being able to speed these things up by exploiting things like sparsity is essentially the name of the game. So VoxelNet came out in 2018. The follow-on work, SECOND, says, okay, what if we exploit the sparsity to speed it up by doing sparse three-dimensional convolutions? So this is from the second paper. This is their example. They actually treat this as a two-dimensional convolution. But the key intuition here is imagine that you have an input where these white slots are all zeros and these colored slots are non-zero. Rather than actually doing the conv over everything, including the zero, you can do a gather where you essentially write down the coordinates associated with each non-zero input, do a generalized matrix multiplication using their scheme. You'll actually just get output coordinates that ought to be non-zero, and then you can scatter these results back into the original space. So the key thing here is if 90% of them are zeroed, you get to skip 90% of the operations, and the little bit of extra overhead induced here is totally worth it. So the other things that's worth noting from the second paper are they modify the regression head of the faster RCNN rather than regressing length, width, and height. They say each class is roughly the same size and sort of bounding boxes, so they just insert the mean. And then they also regress, or rather do classification on direction. So rather than regressing a full 360 degree, they do negative 90 to 90. And then they use this 1, 0 for direction in order to get the full 360 degree. And they talk about this in the paper, and they find that this results in much better results. So that was about the method. Now I'm going to talk a bit about the literature, right? So the paper itself proposes two variants. And then the key change between these two is the size of this backbone, right? The component after the actual input. And the big variant is actually used for all of their performance evaluations because it gets higher quality results, although not by much. And then they do all their evaluation on the Kitty data set. Note that this paper predates the release of these other bigger data sets. And they also come with a bunch of data augmentation tricks, and they find that they get 50 millisecond runtime, right? So they're 2 times faster than comparable or slightly better networks, and they're significantly faster than VoxelNet. Is there a question? Okay, I'm going to continue. So I would say looking at this actual paper is in a practitioner looking at the literature. They do a very detailed description of the approach, right? So they provide full mathematical information about how this thing operates, and they motivate and discuss this angle regression change, right? The thing I mentioned with regards to negative 90 to 90. They explain why this is a failure mode in VoxelNet because of the confusion with direction, and it should be separated out. And they do an ablation study to demonstrate if they don't use their data augmentation techniques, that they get worse performance. And then they actually also provide an open source first-party implementation. This is the lead author on the paper. However, one of the problems is they provide very little intuition about the larger system, right? The system is described. They say, we did this, and this is what we built. But they don't actually talk about a lot of the motivating factors for some of their design decisions, including, for instance, why they chose their backend or why they picked the voxel encoding scheme. So they use the exact same voxel size and configuration that was used in VoxelNet, but again, they don't motivate why this is a good choice. They also don't talk about how much failing to regress length, width, and height actually helps their results. So one of the big things with Kitty is you have cyclists, cars, and pedestrians as your 3 classes. It turns out that all 3 classes are roughly the same size. Right? The bounding boxes are all roughly the same size. So choosing to regress them probably won't help you very much in terms of accuracy. However, this doesn't work in other domains potentially, right? You could imagine trucks being of wildly different sizes, and regressing an average bounding box across all of them might cause a problem. So it's not clear how much of their performance improvements over, say, VoxelNet were due to failing to regress these things. And they also don't provide any sort of data runtime on the different components of the network, i.e. how much time is spent just in convolution versus their backend versus whatnot. And this is of value to practitioners because they would like to explore this quality runtime trade-off Pareto frontier that I talked about earlier. So they also, finally, don't provide any intuition about why they made the changes that they made in order to create the big variant and small variant. They simply said, we did this, and the small variant, a little bit worse, twice as fast. So with that, I want to move on to the second sort of representation encoding in this taxonomy, which is bird's eye view. So the 5x5x5 voxel grid example that I had before, right? We were actually slicing not only in horizontal or right X and Y, but we were also slicing in the Z, right? They were taking vertical slices. But I think a reasonable question to ask is, what if we didn't slice the scene vertically? Right? One of the things that you have by operating in the real world is we have gravity, right, in the vertical axis. So very rarely is it the case that there's relevant objects that we care about stacked on top of one another. And so it's not really the case that you're going to see cars floating in the air 5 feet off the ground or also like near the ground plane. So to that end, what if we didn't slice vertically and we essentially make voxels of infinite height, right? And so this will allow us to essentially have what we call pillars. So they have a length and a width, and then they're super tall. Like with 3D voxels, they are scale invariant. And like with voxels, they're able to reason about negative space and handle occlusions well, and exploits this lack of vertical object stacking in the real world. So roughly, there's going to be one object per vertical slice, and so this isn't something that you have to worry about. And this representation is going to still be sparse, like with the 3D voxel. So the neat thing about this is because you can then take these, vectorize it, just like you did with the 3D voxels, you're able to essentially run just straight up 2D convolutions over the top, right? So you take your input, convert them to vectors, you can run 2D convolutions from bird's eye view, right, the top view, and pipe this into the rest of your network. So this is essentially an overview for PointPillars, which is directly built on the sparse encoding of second. So you can take your point cloud, you extract pillars, you stack them, you then run your PointNet over it to do learned feature extraction, and what you get out is a pseudo image, right? Where the pseudo image refers to this because it's essentially akin to taking this, rotating it on its face, facing you, and it's just like the RGB image, except rather than being just 3-channel RGB, it's n-channel depth. It's able to run PointNet by doing sparse convolutions on the sparse 1x1 convolutions on the essentially stacked vertical representation. And then it's able to feed this into a standard 2-dimensional backbone. They show this here. And then they feed it into SSD, which is a single stage detector, right? They chose to use that to replace multi-stage faster RCNN. So rather than having a region proposal network and then doing refinement, they do it all in one single stage. So in this literature, right, looking now at the literature as opposed to the method, right, they propose multiple variants, and they do this by changing the XY size of the pillars. And this allows for a trade-off between the speed and quality that we talked about before. And again, they also evaluate directly on Kitty. So they actually talk about additional data augmentation techniques, right? So this is extending off of the data augmentation from second. And they're actually able to get 3 times better performance than second while getting comparable results. So this is actually exciting because this is fast enough for 60 hertz performance while being state-of-the-art in terms of quality. And they talk a lot about the sort of engineering decisions that they made in order to get there. And for instance, one of the things they talk about is exploring the NVIDIA TensorRT runtime in order to get significant speed up over PyTorch's runtime, right? They would be comparable to the speed of Smaller's version of second if they didn't use TensorRT. So they actually provide this really nice plot in order to reason about mean AP on the bird's eye view problem for Kitty. And then they compare against second And they're able to show essentially this trade-off where you can get right over 100 hertz operation while being of higher mean average precision. So really, what are the pluses that come out of this literature, right? The ablative studies that they do are really in depth, and I think that they speak a lot to the motivations of the authors who are actually a self-driving car company, right? Nutonomy. They look at changing the pillar size. They look at shrinking down their vectorizer and comparing it to previous results because their vectorizer is significantly smaller than that used in second. They also do an exploration of this MAP versus speed frontier, which I just showed you. And they talk about the data augmentation changes that they do in depth. And they actually demonstrate that even if you just port those back to second, you get better results. Finally, one of the neat things that they talked about there is component runtimes. So they actually tell you for each section of the network, how long it took. And this is really nice from a practitioner's perspective because you then now know if I want to make this network run faster or trade quality for speed, where should I start looking? And eventually in addition, they also provide a first-party implementation done in actually a fork of second. So this is on their GitHub page. Probably my only real complaint about this paper is they don't do any discussion of why they chose the SSD detector. Presumably, they found that it had better performance properties, but they didn't really talk about what those properties are or what another detector, if you wanted to replace SSD with something else, should bring to the table in order to provide these properties. They also don't discuss what, if any, further changes can be made to the vectorizer. So they run an experiment where they made their vectorizer significantly smaller, stuck it into second and said, hey, look, we get the same quality results inside second using our smaller vectorizer. Our smaller vectorizer is better. They didn't indicate that they tried any other vectorizers that were even smaller and worked worse. So that's an open question is, can you make the vectorizer even smaller? So finally, the third representation I'm going to talk about, and this is somewhat different than the previous two, is a range image representation. So you can see a picture of this scene and a LiDAR return depth readings. And this is placed into essentially a two-dimensional image where color represents depth, right? So it's like an RGB image, but usually the pixels contain information on range as well as intensity. One of the things that you might immediately notice is that this is a very dense representation, right? You get some of these weird blue artifacts due to no returns, but for the most part, there's lots of data contained right next to each other. So you don't have to do any of this sparse bookkeeping, which makes implementations difficult, number one, and two, can cause a lot of overhead in actual computation. Some of the downsides of range images, as I mentioned before, are as you get further away, the distance between the pixels gets larger, right? This is just a natural result of casting points further away. So your model needs to learn how to deal with scale variation. And as you can see, for instance, this car is occluding the back half of this other car over here. Your network just needs to learn how to reason about that negative space, which isn't encoded directly in the encoding of, say, the pillars or the 3D convolutional voxels. So this LaserNet essentially takes a height map, an intensity map, the range map. They also take in like azimuth, right, actual angle that the readings were taken at, along with whether or not there was actually a reading returned. They feed this into a CNN, which we're going to talk about in a moment. And essentially, they then regress per pixel not only a box per pixel for the full class, along with a classification, estimated classification of what that box is. They also estimate corner variance, right? So you have a full range image, and what you get out is essentially a range image worth of boxes on a per pixel with corner variance. They then engage in clustering, where they actually take into account, they use a custom algorithm they developed where they take into account the estimated variance of each of these boxes in order to merge them into like a better notion of uncertainty using their adaptive non-maximal suppression. And ultimately what they then end up spitting out is a per instance box with actual variance estimates of like how certain they are and how much this can change. So this is the CNN. This is this architecture was taken from what's called a deep aggregation network. So this is like fairly common in 3D representations for range images, because one of the things that it lets you do is essentially reason about data at different scales while keeping around the reasoning you did at a different scale, right? So I'll expand on that in a second. But essentially, each of these boxes, right, blue and green, correspond to what are honestly fairly large networks in and of themselves, right? They're all comprised of basically convolutions with skip connections, right? So these are ResNet-like. And ultimately, what comes out when you're done is this single output. So this is sort of reminiscent of, these are called image pyramids. So these were used in classical vision. The idea being that, going back to the classical convolutional feature extractor, if you wanted to do feature extraction on an image that was close and then an image that was far away, you might fail to extract the same sort of image. So if you take this close one and shrink it down, you're going to be able to extract out the same sort of features because they'll then be at the same scale farther away. And so that is essentially one of the primary purposes of this deep aggregation network, is to try to be able to get this sort of scale variance to naturally be learned and pop out of this network. So, and thus handle the scale variance associated with this range-based input encoding. So this paper, right? So this paper was done by Uber ATG. They proposed a single variant that has a 30 millisecond runtime. This takes longer than PointPillars, but less than seconds large mode. And they evaluate on 2 data sets. They evaluated on Kitty. They got poor quality results on Kitty. They claimed that this was due to Kitty's insufficiently large size, being unable to train their very large network. And then they also evaluated on ATG4D, which is an internal data set owned by Uber. No one outside of Uber is allowed to see it or train any of their models on it, but they claim that they got good quality results, but they only compare against other Uber ATG methods. And this has been a running trend in all of their papers that talk about this ATG4D data set. And I actually asked some people who work in industry to know if this was ever made available to anybody, and their answer was no. They just started talking about it in a paper one day, and that's how they compare all their stuff. So in order to back up their claim that Kitty was not sufficient to train their network fully, they built a CDF distribution of essentially what the network was estimating in terms of confidence or variance on the corners of the boxes relative to what it actually ought to have. And so what they can see here is that Kitty is overconfident in areas where it should be low confident, and underconfident in areas it should be higher confident, right? That's essentially what these curves mean here, because it's all trending towards the mean, which is like, if you have an uninformed prior, you just guess 0.5 all the time, and that's probably going to be acceptable. Whereas they say on the ATG4D data set, they're much better calibrated, right? They have a much better sense of predicting these sort of bounding boxes because their network has been appropriately trained. So looking at this literature, right, what are the pluses from it, right? It indicates that regressing uncertainty in bounding boxes, if you have sufficient data, is probably a good thing to do, right? They do spend a lot of time talking about their adaptive non-maximal suppression and the value that this provides, particularly later in the pipeline, because now you don't just have bounding boxes, you have regressed uncertainty estimates. And they also talk about how the range image representation is really useful because it's directly usable for other components of the pipeline. However, I would say that looking at this literature specifically, one of the primary drawbacks is that it doesn't have any sort of good performance on any data set that you're able to evaluate on, right? They hide the data set that they performed well on. They perform poorly on the one data set you can test it on. And they just say, oh, well, our data set is sufficient and Kitty is insufficient. They don't provide any sort of additional information about, if you wanted to train this on your own data set, what would you need to ensure, what properties would you need to ensure of your data set in order to get it to be perfect, to be reasonably well calibrated? They also don't really perform any ablation studies. They claim in the paper, we removed this feature and it performed worse. And they did this for 4 paragraphs in a row. But they provided no evidence or no discussion of like what the results were relative to with the feature. And they don't actually provide any sort of information about how non-Uber ATG methods would perform on this private data set. So for instance, it would be nice to know on the data set that this thing performs well on, how well does it perform relative to, say, PointPillars? Well, I don't know. And they don't provide any sort of information on the runtime for each component. They mention how long inference takes for their full system, or sorry, inference just for the convolutional network, and then runtime for the full system, but they don't break that down any further. So one of the questions you might ask is, can you make this deep aggregation network smaller? And how much of a quality hit will you take? They don't provide any sort of this information, nor how much of a speed up would you get. So that is essentially the review of the 4 papers that I wanted to talk about as part of this WPEII. I think an interesting question to then look at is say, okay, I'm a practitioner. I want to build a robot in the real world, and essentially this is the literature review I did. How does this literature help me in actually going about executing on this task that I'm given, right? So as an example task, imagine that your goal is to build an indoor-outdoor robot, right? As it's driving around, say, campus, doing deliveries between different buildings, you need to avoid oncoming cars. You need to not cut people off. You don't have guaranteed Wi-Fi, so you can't do everything off board. You also need to have low latency responses to avoid oncoming traffic or people cutting in front of you, things like that. You can't run people over. And you need to reason about things like sensor characteristics and worry about your limited compute on board. So I think I've made it sufficiently clear that the literature as shown doesn't provide all of the information that you would need as a practitioner in order to just pluck out of a hat, I should use this thing, this one's clearly better for my application. And I think the essence of why is the problem formulation that this is solving, right? The one that we talked about, different at the beginning, is fundamentally different than the problem formulation that's found in these sort of real world systems. So that is sort of the motivating factor behind the last section, which is where do we go from here in order to make it so that these things are more heavily aligned, right? How do we address the sort of shortcomings in the present literature so that these methods are more directly applicable to these real world problems? So I think the first thing that's maybe the most glaring is the fact that the evaluation metrics that we talk about don't actually consider runtime as well as quality in a single high-level metric, right? You could go and pick the highest quality detector, right? The one with the best results, and then you look at and then you eyeball its runtime and you compare it to the next best. How do you decide which is actually better for your application? So streaming AP was proposed by this Towards Streaming Perception paper. Essentially the notion, this is taken from the vision literature, or the two-dimensional image vision literature, where really what you should be evaluating on is at the time step where you actually take in the observation and start computation, you should be comparing not against the input image, but against the output image when you finished your computation, right? If it takes you 3 seconds to process input A and then you spit it out, the problem is B is what the real world looks like now, and this detection is useless. And so it might actually be better to have a far worse quality detector that runs way faster because you'll get a better representation of what the real world actually looks like. And that is encoded in sort of this streaming AP. And it's fairly straightforward to take this metric, bring it to the literature for 3D object detection, and start doing these sort of evaluations on, say, the Waymo or Argoverse or Newtonomy data sets, because all of them provide clips. And so you can actually do this time-based evaluation, which is not something that you necessarily can do on the Kitty data set. Another perhaps obvious thing is, rather than reasoning about a single image, you might choose to reason about multiple frames of image, right? There's motion information that is encoded in these sort of successive representations. For instance, an object might temporarily disappear behind something. Having these multiple time step representations will allow you to better detect objects even if they're not super visible in this single shot scene. Additionally, one of the things, and this kind of goes back to the streaming AP problem, is you actually might want to make decisions online about whether or not your bounding box is one of sufficient quality, or two, you need to make a decision right now or you have more time and you can wait. So if you're driving very slowly, you might choose to spend more time doing computation in order to get a better answer. But if you're moving really quickly or you need an answer right now for safety reasons, you can choose to stop this computation early in an anytime algorithm. So there's some early work on making these sort of anytime algorithms, right? This was a master's thesis out of CMU, where you essentially use an RPN in order to detect a broad area that has an object in, and then you do iterative refinement using a PointNet. Additionally, right, reasoning about sensor realities, one of the things that is a reality with LiDAR is there isn't a global shutter, right? It actually takes vertical slices as this sensor is physically spinning, and these tend to take observations at about, global observations at about 10 hertz. What that means is if you wait for a global shutter, right, if you collect all of the observations from an entire scan, the very first observations are going to be 100 milliseconds old. And this is probably not ideal if you want to have a highly reactive system. And so you might imagine doing either streaming-based approaches where you directly stream these off the sensor and directly reason about it, as this paper does, or you could imagine packing them into wedges. So rather than waiting the full global shutter, you could wait in chunks. And this would provide, for instance, the ability to store significantly less of the data, which would allow you to also represent the scene in a smaller and more compact way, which would use less VRAM, going back to the resource usage. One of the other things that you have available in these sort of holistic systems is additional information about the environment. So for instance, you actually have a map. The map tells you about relevant things that might be upcoming. So for instance, if there's an intersection up ahead, you can know that this is something that you really need to pay attention to. And you can actually choose to spend more of your computation time worrying about that rather than processing the like leaves on the tree in the corner over there that you know you're never going to drive over there. It doesn't matter. And there's sampling-based approaches in order to like try to get diversity of the scene in order to process it as a whole, right? So DPU voting, that's the paper down here, is an example of something that is sampling for diversity. You might choose to also bias this sampling towards areas that are of importance. I also think that, and I haven't really seen this done on a large scale, this is somewhat done on a small scale, that there's a place for system level fusion of detection and prediction pipelines, right? So the reality is in these robot systems, there's not just a vision pipeline and that's the only problem, right? You also need to worry about making decisions. You also need to worry about estimating how other agents in the environment are moving and these sorts of things. If you can build a shared backbone that's directly able to leverage both of these things, then you're actually able to share the compute budget and you're less likely to have a case where one system knows about an object, but the other system doesn't. And so you get these like bizarre behaviors as a consequence because you have discontinuities in understanding of the scene, right? This paper, which was posted a couple of weeks ago in arXiv, essentially tries to do panoptic segmentation as well as estimating how those segmentations are going to move in the future. So this, I think, is a stab in that direction. So with that, I will conclude my presentation. Thank you. And I hope that there is a lot of questions as well as points of discussion.